to welcome everybody to the first MAP podcast. At this stage, we haven't decided whether MAP will stand strictly for Malaria Atlas Project, or if it might be more generally maximum a posteriori, because the idea of the podcast is to talk with people like our guest Sam today about the statistical methods which we use to map malaria and other diseases. And so sometimes that'll mean talking specifically about epidemiology, and other times more about mathematical statistics and probability theory. But we'll see how this evolves depending on the success of this episode and how well Sam does as a guest. So let me introduce Sam properly. His name is Sam Bhatt. He's a lecturer in geostatistics at Imperial College London, and Sam was one of the first statisticians to work on the Malaria Atlas Project. So he'll tell us a little bit about that, and then we'll get into a conversation about the type of statistical methods which Sam's been working with most recently, and how he's using those to improve our mapping of malaria. So Sam, welcome.
Thanks for having me on.
I'd like to start by asking you about how you came to work for the MAP team, and what your background was in terms of what you did for undergraduate degree and your PhD studies. So how you came to get into model-based geostatistics.
So I change fields quite often, as I think many people have in the Malaria Atlas group. No one's really an epidemiologist or really a statistician. Everyone seems to come from somewhere else. I did my undergraduate in chemical and bioprocess engineering at Bhatt. Found that I really disliked engineering and wanted to change to something a bit more computational and a bit more technical. And did a master's in computational biology. It was a part 3 type master's at Cambridge, and really enjoyed that and thought, I'd like to pursue some more research. And started a PhD in Oxford in statistical genetics, in viral genetics, which was a really nice field and allowed me to learn more technical details. But
so that was in the zoology department?
That was in the Department of Zoology, yeah, with Professor Oliver Pybus now.
Right, yeah.
And then that was looking at adaptation and very, very different type of statistics to the kind of stuff we do in MAP. But still, the main interest that I had was in stochastic processes. And like many people who love statistics, you start gravitating towards the field that you actually like, rather than just, say, doing an undergraduate in statistics and continuing in that vein for your entire career. And then I came to work with Simon Hay, one of the founding members of the MAP group, and with Pete Getting, the current head of the MAP group.
That was as a postdoc?
That was as a postdoc, yeah, and I was working on dengue. And initially the idea was to build spatial models for dengue, so not really what we've done in the Malaria Atlas Project, and a little bit more machine learning and less about stochastic processes. And finally an opening opened in Pete's group. I was Pete's first postdoc in the Malaria Atlas Project, and we started working together on the big new steps for malaria, specifically trying to figure out what the hypothesis we're trying to figure out was what has been the change in malaria from 2000 to 2015 in response to interventions. Because as you know, but perhaps many of in the audience don't realize that over the last 15, 16 years now, there's been a huge international effort in terms of technical capability and in terms of raw input of interventions into African countries to try to drive down malaria. But as with many of these policies, the scale is so large that to actually measure and scientifically test what was the effect of those interventions is quite challenging. And so that's how I came into MAP, and that's my background. But my primary interests are in statistics and machine learning, as much as I can manage.
Right, so I'd definitely like to ask you a bit more about the methods you used for the dengue paper later on. And being very modest, I know that you didn't mention that in fact that dengue work led to a Nature paper, first author, very impressive. But so I think perhaps for some of those viewers who are not familiar with the actual Malaria Atlas Project itself, I was wondering if you could tell us just briefly what is the nature of the project. I mean, for people who really haven't heard much about it, the acronym Malaria Atlas Project map suggests that maps is something that we're making.
Yeah.
Could you tell us a little about how we make those maps, just broadly, and then who are the end users of those maps?
Yeah, excellent, yeah. Well, I mean, there's a bit of history behind it. Initially, when the Malaria Atlas Project was started, it started in zoology with David Rogers, who was looking at remotely sensed data. And remotely sensed data is when a satellite flies across the Earth and measures something at a very high resolution, say the amount of infrared reflected back as a measure of greenness.
Yeah.
So the Malaria Atlas Project initially looked at the changes in greenness in the highlands of Kenya and tried to figure out, well, how was that linked with the resurgence of malaria. Following that, MAP started a huge data trawl effort where they tried to collect data from published data sources and from everywhere possible. And from that, the idea was to build a statistical model that could actually map out measures of malaria. Now, when I say malaria, that's a rather vague concept. What do we actually want to map? We need something that's epidemiologically relevant. Things like incidence, the number of new infections of malaria in a given time, or what they call the entomological inoculation rate, which is the number of times an infected mosquito bites an individual over a period of time.
Definitely sorry, just to interrupt, that epidemiological inoculation rate was a fascinating concept for me when I came from astronomy to study malaria. So entomological inoculation is obviously the mosquito is the vector which inoculates with sporozoites the potential human host.
Yeah.
But when I was sort of from a quantitative perspective, when you start getting into malaria, it's fascinating to see the scale of the actual number of bites that is represented by the epidemiological inoculation rate. And indeed, in some places, you'll have the EIR is 500 bites per person per year. I think that's it just to me seems incredible. And that's not 500 single mosquito bites. That's 500 potentially infectious mosquito bites.
And that's the scale of the problem we're working with in Africa. And it's actually unbelievable quantity. What we do map out is prevalence,
right?
Which is when you go to a village and you sample the number of individuals using these rapid diagnostic tests. They just take a blood spot and they determine whether you have the malaria parasite in your blood out of the total number. So it's a simple binomial variable. When you look at that measure of what they call prevalence, it's the ratio of those two, or parasite rate, they're all the same term. It doesn't give you the understanding that EIR sometimes does in terms of you can have a prevalence of 100%, but that's still, again, based on the sample that you have there. And it doesn't tell you something about the force of infection in the same way that EIR does. So it is quite mind-boggling to have places which have 500 infectious bites per person per year.
Absolutely.
That's in the absence of any interventions, that's either your immune system gets it or you ultimately have to pass, which is a sad state of affairs.
Yeah. Really. I mean, I don't want to get too sidetracked, but
no. So the maps. We choose a measure which map traditionally has been using prevalence, standardized to an age of 2 to 10 because that's epidemiologically relevant, and then we use Gaussian process regression and we build a bunch of maps, and ultimately those maps are predicted at a 5 kilometer resolution, and then they are disseminated to either other modelers to use it as a starting point for the force of infection, but more often nowadays we work directly with countries to actually give them an idea of which areas are high, which areas are low, and where intervention should be put in. We also use these maps to give big, large statements for the WHO. We're a WHO collaborating center, and try to assist the WHO by giving them information about what are the changes and what is the current state of affairs. So we contribute a lot to the World Malaria Report every year.
Yeah. So for end users, it's a broad spectrum of people, like both the malaria control programs on the ground, as well as these supranational organizations like the WHO. And
other research groups as well, which helps validate our work. And once you have a force of infection, you can then give it to a modelling group, such as they have at Imperial or at the Swiss Tropical, and and they can then use that as a starting point to then run a bunch of simulations, which can then again feed back to countries.
Yep.
So it's all one big academic community that gets along pretty well.
Yeah, certainly when we were up at the MMC the other week, which stands for Malaria Modelling Consortium, it was very interesting to work with the modelers and as far as deciding or determining what we could supply in terms of maps of existing transmission to support their studies and projections as far as how malaria might develop under different interventions.
Yeah, the consensus and the whole international community's urge to move as fast as possible to elimination. It's really great, and I think the modelling does have its place in there, along with working directly with countries to actually get things done and get modelling products used. There's no point in just getting a paper out that none of the countries actually use, and it's just of academic interest.
Absolutely, yeah. Yeah, so we've talked about the products which go into making the maps. We have satellite images, which provide things like rainfall, temperature, different environmental measures, or to be more precise, I should say proxies for rainfall, because as our geographers will point out, it's very difficult to construct a good measure of rainfall. In any case, we have these high-resolution covariates, and we also have measures of prevalence or perhaps some other different metrics like the entomological inoculation rate. And so we're going to take those two, and then the statistical model comes in what particular way?
Well, the statistical model is Gaussian process regression, which is a huge method now in machine learning over the last 20 years. It came back from relative obscurity, if it ever was there, and it's been used in a wide variety of applications. Now, the reason that Gaussian process regression is so useful is that, first of all, it takes you have some data, and you have a likelihood that, say, describes that data. For example, when you have number of positive out of number of total malaria individuals, you'll use that, a binomial likelihood, to describe that. But you want that likelihood to be parameterized by an observational model. And the observational model, we use the Gaussian process or stochastic process. And the Gaussian process is, in its formal definition, well, let's just go with the informal one just for the audience. You can just think of it as a multivariate normal. So it has an underlying mean, but then it also has a covariance function. And the covariance is helping to describe a similarity measure. That's what it does. So in the application for malaria mapping, we use that covariance measure to measure spatial correlation or spatio-temporal autocorrelation.
Right.
And the reason that this is so important is for malaria is that while you use measures of greenness and measures of urbanicity and all of these other factors to describe a certain mean prevalence, when you look at what's left behind there, there's still quite a lot of structure. And if you can account for that structure, then you can greatly improve your predictive capacity and improve how well your models can predict new areas. And so leveraging this spatial correlation or spatio-temporal correlation through a Gaussian process provides a very, very solid model for disease mapping in this context. And that's initially what was done in the Malaria Atlas Project. In fact, the original Malaria Atlas Project maps were looking just at spatial autocorrelation. They didn't include any covariates other than urbanicity.
So this is going back to Pete's 2008 map?
This is going back to, Pete and Simon's 2007 map.
Yeah.
And then, of course, the next iteration of it in 2010, I believe, was including covariates as linear terms.
Right. So initially just using the Gaussian process purely to do all the heavy lifting, and then helping out subsequently with the covariates?
With the covariates,
I hadn't even appreciated that myself, actually.
No,
the beginning was just with the GPs.
It's quite unbelievable, actually, and so, you use the Gaussian process to essentially get the spatial autocorrelation, but then you can parameterize a mean function on there as well,
Yep. So how do you think our mapping has evolved as far as, certainly in this historical context, we started just with using the GP to do all this heavy lifting, and then we add the covariates to help improve our prediction of the mean. What do you think has been the most important developments, without leading the witness? I'd perhaps throw my hat in the ring to say the Inla software has been particularly important.
It's been particularly important. I mean, when Pete and the original MAP founders started doing this Gaussian process regression, they were running into two of the most fundamental problems with working with Gaussian processes. First of all, when actually evaluating predictions or actually fitting the Gaussian process, you have to invert a matrix. Now that matrix is the data times data size. So if you have 10,000 data points, you have a matrix with 10,000 columns and 10,000 rows.
Right.
Now, to invert that matrix has a complexity of n cubed. So it scales as if you add 10 more points, it scales to the cube. And so it quickly becomes unbelievably difficult to actually invert these matrices in their full dense form. And so a large amount of literature in Gaussian processes has been to solve this issue.
Right. The second, to look for scalings, computational cost scalings, which are less than n to the n cubed.
Exactly. Yeah. And in my view, Gaussian process regression is a fundamentally Bayesian approach. Non-Bayesian equivalents go by the name of kernel ridge regression and methods like that. And so to evaluate the posterior again becomes the second challenge, which is to use, in the original sense, Pete and the rest of the MAP team used a Gibbs sampler.
Right.
Which was very slow, very inefficient, suffered from huge autocorrelated effects, which is a huge problem. And these two issues were absolutely deal breaking for the MAP project. I mean, this is little known to everyone. I think the original MAP models were run on the Amazon Elastic Cloud for several months.
Right.
Which doesn't give you the flexibility to try out different models and different parameterizations. And it was very, at least as we refer to it now, vanilla.
Yeah, and certainly just that month-long timescale to run a complete simulation and start to get an idea of whether the model has actually fit correctly, whether everything looks plausible. That whole process of model testing, it's really difficult to conduct when you have such long run times.
And depending who you speak to, if you speak to the Stan bunch, they'll claim that those posteriors, even if you run them for that long, will still be
because of the Gibbs sampling.
Because of the Gibbs sampling, won't solve the pathological problems of the actual space that you're trying to explore. Right. So you're getting almost the worst of both worlds.
Right, long run time and
perhaps not even a convergent solution.
Sampler with a difficult to diagnose convergence, right?
So it's unbelievable. So Inla came in, and for those who don't know, the Inla is just it's a glorified and really well programmed Laplace approximation, where essentially you're putting a Gaussian over your posterior, centered and rotated as best as you can. But the other great revolution of it was Finn Lindgren came up with this stochastic partial differential equation formulation.
Right.
Now, the covariance function that's being used in these Gaussian processes, and so the covariance function describes how the similarity and distance between 2 points decays as time goes by, how smooth that is, how rough that is, what the functions look like on the shape of that.
Right. Makes effectively a geometrical. It places some kind of, I suppose, geometrical shape to the expected noise. Is that a fair way to say it?
Technically, yeah. I mean, it defines a set of functions that could represent the spatial autocorrelated structure. It allows these functions to be jagged, smooth, and vary in different ways. And these functions, of course, stochastic processes in their own sense. So what Finn did was he figured out that there was an explicit link between these Matern covariance functions that are used in spatial mapping. In fact, it was Peter Digley who first introduced and said how appropriate the Matern is for spatial mapping.
Right.
It doesn't have concentration of measure problems that the more common squared exponential or Gaussian kernel have.
Okay.
It has a lot of flexibility.
It's easier to produce a well-conditioned covariance matrix. Sometimes the squared exponential runs into some problems.
We always have to put these jitter, but that's just something everyone ignores.
Or another trick I've seen is to raise it to the power of 1.99 instead of to the power of 2.
That's right. Yeah, just to get the matrix to be fully ordered to be a positive definite, which is the requirement.
Right.
For a covariance matrix. So Finn found the explicit link between a stochastic partial differential equation from Whittle and the Matern, and found that a weak solution to the stochastic differential equation solved through Green's function,
Mm-hmm.
can be made to be Markovian.
Okay.
And so the solution to the stochastic differential equation at a set of nodes
Mm-hmm.
can then provide a skeleton for that actual maternal field with extremely high accuracy.
Right.
Now, there are a large number of benefits for this. First of all, reducing your problem, say, from 20,000 points to 500 nodes,
Mm-hmm.
and then simply evaluating the field at those nodes and then interpolating
Right.
into different areas reduces the dimensionality of the problem hugely.
Right.
And this is an absolute game changer. But also, the interesting statistical part of this is that Finn's SPDE model was a generalization of the very famous BSAG model,
Right.
the conditional autoregression model, except in continuous spaces, something that I think BSAG would have loved, and I think Finn thinks that too.
Yeah.
And so you can then use Gauss-Markov random fields, which have a large number of very, very good computational properties and help reduce down that complexity of O(n) cubed to something much, much less.
Right.
And you can truly keep following this down the pipeline and in some way have really close to linear properties
Mm-hmm.
with the SPDE model. And then the SPDE model can be made into spatiotemporal models, and in INLA the way they do this is through Kronecker products.
Mm-hmm.
But you can do a Kronecker product with many other different functions, but generally in INLA it's done through the AR1 function.
Last night I was boning up on my INLA knowledge, and in
yes.
fact I had a look at this 2017 paper, which is something of a review.
Yeah, the
Havard
review, yeah, just came out
review
recently,
is right. So Havard Rue is one of I think the first author, and that was interesting because first of all it gives a very good summary of some of the recent
Yeah, it's a fantastic paper. Yeah.
recent applications of INLA in disease mapping, but also various financial or other types of studies looking at map making and also time series modeling. But one thing that I was reminded of again that I tend to forget is the just how efficient the Laplace approximation is in scaling, in terms of scaling with number of data points. So for this under an IID sampling scenario, which of course is unlikely to be the case for a true spatial mapping problem, but just for the vanilla example, it's the convergence of the Laplace approximation is in power n, or of order n, which is quite impressive compared to ordinary Monte Carlo.
Yeah, it is.
Root n convergence.
Yeah, it's pretty great, and there are nice properties of it. I mean, there are problems with it when you're fitting Gaussian likelihoods. It's wonderful.
Yeah.
When you're fitting non-Gaussian likelihoods, this is where the nested part comes in for the INLA, not just the standard vanilla Laplace.
Mm-hmm.
And it still does work very well, but unknown to most, and I think Peter Diggle will be the first one to say this. It does require a lot of expert knowledge to get the tuning right. You really have to be looking at whether your Laplace approximation is actually representing your posterior well in terms of coverage and in terms of the point estimates.
So this is what this tuning is what's gone into the INLA code for the most standard or the most common geostatistical models, right?
Yeah,
so that
exactly.
Within this family of binomial GP regressions, linear predictors, I think much of that fine tuning has been done.
It has been done, and that's great for the end user, so that they don't have to worry about it. But I mean, a huge amount. The appreciation should be that a huge amount has gone into the actual software to actually make it friendly for users to use it. I mean, the only problem with it is sometimes the flexibility can be there because it is a general package.
Yeah.
And there are a large number of models, but you're restricted in terms of how far you can go with that.
Yeah.
But I mean, as we've shown, you can go very, very far with it.
Right.
And ultimately, it's not that difficult to code up, given that a lot of the libraries are already coded up by Hoved, Dan Simpson, and Finn, and the whole INLA team.
So other than the use of software like INLA, what other methods have you been exploring to combat these scaling challenges with the covariance matrix?
Well, so with there's two issues. There's a third issue I should add, other than just evaluating the posterior and the scaling of the matrix. The third issue is actually the predictive power of these models. Right. In that, when you're fitting a normal MDG model I say MBG, model-based geostatistics model,
Right. Yep.
the original models that we did in the Malaria Atlas Project, or are you fitting just a generic in the model?
So just to be clear, generic MBG model would be linear covariate predictors
Exactly.
plus a Gaussian process
Plus the covariance
for
function, right?
for the residual noise.
So you can just think of it as a linear model, but then jointly fitted with a covariance added on there that allows Bayesian shrinkage.
Yeah.
Now, there are, of course, huge deficiencies with the linear model. For some problems, like onchocerciasis, for example, a linear model is an extremely good fit. Then when you add in the covariance matrix, you can get some good results from that. But if you're, say, trying to use model-based geostatistics for mapping HIV, for example,
Right.
you're going to find very, very large deficiencies with the linear model. Because what you're really trying to map is a very complicated, non-linear interacting function where the covariates coming in, such as urbanicity or aridity, are going to act as proxies for socio-demographic phenomena that you don't actually have data to measure. And so the standard in the model takes a linear basis or linear covariate and then fits a covariance function to it. The covariance function choice is always got to be the Matern because you're working with the SPD model. So there are constraints of it. Now I'm saying that's great for application, but sometimes that doesn't work as well. And so some of the work that we've been doing recently is well, actually it's an interesting story. So there was this competition on Kaggle.
Right.
It was basically mapping West Nile virus in Chicago.
So you need to predict it.
We need to predict it in Chicago. They gave you data in 2 years and then had to predict another year. For those who don't know, Kaggle is this competition where you try to get the best predictive score. It's quite fun, but it's impossible to get high scores because you have to dedicate a huge amount of time at it.
Yeah.
But yeah, I threw the, I thought, well, most people on this Kaggle competition will be standard machine learners that do Facebook. They're not really going to be working with the spatial methods in the way that they should. And so I went and I threw the standard spatial techniques that we had at the problem, and actually we did quite well.
So what sort of
we stuck. I mean,
we get in?
Sadly, because I do too much, I didn't continue too much. But yeah, we were in the top 5 or 10%.
Right.
Initially, I should add initially. Things quickly spiral after people do more and more. But I was wondering what on earth are these people doing who are getting the score better than me? We're doing industry standard model based geostatistics. Why aren't we doing better? And combed the Kaggle forums and realized that everyone just uses ensembles.
Okay.
And then thought, well, why don't we see how that works for malaria?
Right.
And the key is this paper by probably one of the greatest statisticians of our age, I think, David Wolport, called stack generalization, which was a way to create an ensemble such that you're trying to maximize your predictive capacity. So ensembles are always quintessentially trying to work with the bias variance trade-off, and adding another term on it, the covariance term onto it, and there's quite a lot of work going into that. But stack generalization comes in, and essentially it's trying to generalize a generalizer. So you have a model, and it predicts a certain malaria surface, and then you add another model on top of that then tries to correct that, but while taking in multiple different types of predictions.
Right, so just to be clear, the ensemble that we're talking about is an ensemble of different models. Depending on the context, some of those could be GPs, which are predicting.
Some of them, they could be.
Perhaps they're not at all. No. Some could be just linear models or machine learning models.
That's the thing, because alongside with Gaussian process regression, a huge amount of work has been going into boosted regression trees, random forests, and they're finding huge applications all over. Mars, multivariate adaptive regression splines.
Your dengue Nature paper was a BRT.
BRT,
regression tree.
And boosting is a truly remarkable algorithm in terms of just how well it predicts. It's truly a remarkable algorithm. And when applied to regression trees, it does very, very well. So but things like random forests are just bagging. They're just averaging, and the way that they manipulate the bias variance trade-off is through the averaging. They're trying to reduce down the variance term on the bias variance trade-off. But as opposed to just simple averaging, we can actually do weighted averaging. So weight different models from how good they contribute towards the final result in the ensemble.
Right.
But when weighting different models, you're going to basically pick the model that most overfits the data.
That's if you're just comparing their within sample.
Yeah, if you're just comparing within
sample.
sample.
Okay.
And this is where stack generalization comes in. And it's a fascinating paper. I recommend everyone reads it. But essentially, what we've done recently is, a paper which, of course, you're heavily involved in, is to use stack generalization approaches to predict malaria. But the key innovation we're looking at is that our ensemble is itself a Gaussian process. So we take multiple different machine learning methods. Mm-hmm. They then contribute towards the mean function now of the Gaussian process.
Yeah.
And then we model any residual variation away from that mean. And essentially what we're doing is, rather than just taking linear terms in the mean, we're going to pass it through a bunch of machine learning methods and predict new, more, I say the word potent, highly predictable mean functions that then you can just, that can generalize a lot better than just a linear basis.
Yeah.
And of course you can expand this, and it creates a flexible framework, and these methods are working very well in a wide variety of applications. They're being used at IHME to map, IHME, the Institute of Health Metrics and Evaluation, to map childhood undefined mortality. I'm using it to map HIV with high accuracy.
Yeah.
And so this has been a great innovation.
So what I had difficulty with initially when we started to think about these, introducing these machine learning models into our existing Bayesian framework, was that ultimately it's not the same as for linear predictors, where you can fit simultaneously the coefficients acting on those terms and the spatial residuals.
Yeah.
Because of the nature of these machine learning models, which themselves are use an internal cross-validation type of procedure to learn their hyperparameters or the controlling parameters. Ultimately, what we have to do is fit first the machine learning models on some portion of data, and then use the stacking to combine them. But the combined result doesn't somehow feed back to the initial fits. So in a sense, we've made a cut to our Bayesian model.
We've made a cut to our Bayesian model, and I mean you can bootstrap to get uncertainty down, but it is not. And of course, you have to tune these models. Tuning a BRT is a hard task on its own. Now, if you choose then random forest, you have to tune that. Elastic net regression, you have to find the lambda parameter. So it does get a little bit more complicated, and you're not linking the two steps together.
Yeah.
But it's as Pete likes to say, it's horses for courses.
Sure.
It's what's best for the purpose. If we're looking for the best possible point estimate, I would throw the stacking hat in the ring and say that it's going to beat most methods.
Yeah, it's interesting.
And it does
for us, because we have a very clear goal, a clear metric to evaluate our work, which is simply predictive accuracy. Sort of out of sample predictive accuracy, which is in some sense easier, I suppose, than some standard Bayesian modeling problems where you're trying to learn a parameter which is inherently unknown and hard to sort of validate your performance other than through simulation. In this case, we have the nice ability to take to use proper holdout samples.
Yeah, exactly.
To compare methods, and so this is, I suppose, the motivation for exploring such unusual fitting methods.
And stacking comes under a lot of criticism because of its people slightly don't understand. There's not a lot of theoretical properties of it. It's one of the things that works in practice.
Right.
I always, people who always try to go with asymptotics. It's helpful for designing algorithms, but you have to be careful not to live in, as they call it, asymptotia. You can't rely on that too much as the design of the algorithms. Practically, the truth in machine learning is models that have very good asymptotic properties behave worse in many cases than models that don't have that many. Just because when you're looking at finite data cases, infinity is very far away.
Sure.
So that's one of the big innovations. The next thing that we've started looking at is, again, on the same vein of trying to get away from this linear model, but in terms of a whole general fitting algorithm, is this new method. I say new, it's in 2007 by Ben Recht and Ali Rahimi. It's called random Fourier features.
Right.
Now the idea is that if you're deriving a point estimate for a Gaussian process through, say, a ridge estimator, kernel ridge estimator, you can solve the optimization problem in either the primal or the dual space. So the primal space is what people are most used to seeing in terms of linear regression, least squares. The dual space ends up getting a big matrix that you have to invert, but has quite a lot of nice properties with it. Now, in the days of small data where these methods first came about, the dual space was fine because there wasn't enough data, it wasn't presenting problems to actually have issues with matrix inversion.
Mm-hmm.
But there's been a wholesale switch now to looking at methods in the primal space now.
Mm-hmm.
Now, how random Fourier features come in is they're saying that, well, okay, we have a certain kernel, and kernels and covariances are
the same
right? We have a certain kernel, and that kernel is defined by a positive definite function, right? Now, Bhatt's theorem says that any positive definite function admits a spectral density.
Right.
And to get that spectral density, we can evaluate it using a Fourier transformation.
Okay, so this is a representation of the covariance
It's a set of features or a set of bases in Fourier space. Now these features, we have that integral, that annoying integral to solve in the Fourier transform.
Mm-hmm.
But as with everything in computational stats, we just Monte Carlo approximate that integral, and that's all that this. I don't want to belittle the achievement; it's a fantastic achievement. But that's all that Fourier features is.
Right. So it's sampling modes from the Fourier space
exactly
randomly.
Just it's sampling from the spectral density, and then using those spectral densities to essentially evaluate the covariance, right? Yeah. So what that means practically is that you have this covariance function or this Gaussian process or this kernel, and you put it through a random Fourier black box. Say that now, you can read up on the paper and read more about it. And then it's basically a bunch of signs, an addition of sines and cosines in solving the Fourier integral for the e to the I, but then you drop the complex part, you just keep the real parts. But all that does is it translates this kernel into a set of basis functions or a set of features.
Right.
And then you just learn those features by linear regression, and you add a regularizer, so ridge regression on it. And so this simplifies the problem hugely. There's a lot of people who can't get their heads around Gaussian processes,
right? But
know linear regression very well.
Yes. Yeah.
And of course, there's no reason why you can't do Bayesian linear regression.
I should say, and have very fast tools for doing a linear regression model.
Very fast tools, from the pioneering work of Boyd and others. There's amazing methods to solve this. And what we do now is I put all of this into Google's platform, TensorFlow.
Right. Yeah.
Which again is GPU compatible and can deal with these large bits, and we can solve this using gradient descent now because we can easily batch the problem in terms of linear regression, and so that's fantastic from our viewpoint because we can sort of now look at kernels which are 30 or 40 dimensional. Everyone looks at space and time,
right,
and thinks, well, that's how you define a covariance function. But why not space, time, and greenness? Like ultimately, you're regularizing the problem. And you're using Matern kernels which have a student T spectral density and have good concentration properties, so you can actually evaluate these functions in 10, 15, 20 dimensions.
Right.
And you get much better predictive capacity, but you also introduce spatiotemporally varying covariance by the very nature that you have this interacting non-separable spatiotemporal covariance function. And this is fantastic, and it's something I think that nobody really does in the field, because a lot of people's INLA is inextricably linked with the 2D, and then you can make it into a temporal phenomenon. So everyone thinks that autocorrelation should only be this two-dimensional phenomenon. Of course, I'm happy to be told this is all nonsense, but the proof is in the pudding.
Yeah. So I guess the first thing that strikes me as being potentially problematic, excuse me, is the dimensionality of the parameter space. So when you have a Gaussian process or a kernel trying to learn distances in a very high dimensional space, I suppose you'd hope that some of those dimensions could be eventually ignored, so that the notion of distance between points becomes smaller in a sense.
I mean, there's quite a lot of work in deep learning about this. It's a recursive dimensionality issue, like how do you actually evaluate this kernel? All local kernels, ultimately, anything other than deep learning suffers from the recursive dimensionality, and all local kernels will suffer from that, right? The key thing here is that we regularize the problem, and so that we're actually not looking at that huge 30-dimensional subset, we're actually looking at a subspace thanks to the regularization of it. And this regularization actually works very well. And in practice, it works very well.
Right.
It's one of the
And
things.
is it a Bayesian regularization, or is it
Well,
more,
currently
I'd imagine a heuristic one based on some kind of cross-validation?
Currently, I mean, in the TensorFlow, you could do both.
Right.
But currently, we're doing frequentist.
Okay.
But you could just put normal priors on it and evaluate a posterior using Hamiltonian Monte Carlo and do Bayesian regularization as well. There's no problem with that. They're the same. But the other key is that in the work that we do automatic relevance determination. This is where you shrink the length scale across either of the dimensions for their importance. But I funnel that shrinking through, because the shrinkage have to be positive.
Right.
I put them through the reticulated unit, which is just a reticulate function is the max of 0 in x. And so it's just a straight line that then has a discontinuity at 0. And people in deep learning use this because it promotes sparsity in neural networks.
Right.
And again, it promotes sparsity in the bandwidth parameters. So if there's truly an insignificant dimension, that can just go down to 0 and be regularized out, right? So you end up with both regularizing your actual function to prevent it from being too complicated in those three dimensions. You put reticulated units in to regularize, not really regularize, actually not regularization, but you put that in to encourage sparsity in the bandwidth.
Yeah. So it sounds sort of like an L1 sparsity penalty that you're achieving more with a sort of a secondary processing step.
Yeah.
Maybe I'm not getting the right idea on that. But.
Well, yes, it's essentially, it's more simple than that. It's just you have a parameter for a bandwidth, and you can't let that be negative.
Okay.
So you're not going to take the absolute value of that.
Yeah.
You could take the soft max of that, so that it has a smooth sliding down to 0.
Yes.
Or you could take the reticulate, which is a very hard boundary.
Right.
And that just, you're basically forbidding that parameter ever be negative.
Okay, sure. Yeah.
It's just as simple as that.
Yeah, I understand now. Okay.
Yeah,
I got you.
It's probably we all used to thinking in a Bayesian framework. And in figurative one, you just throw these hacks at the problem and just let it solve. So you do those things, and then you can use a Matern covariance function that has much, because the spectral density is a student T, and the student T has much better concentration properties than the Gaussian. But I found using the Gaussian gives you better predictive capacity and very reasonable results.
Right.
It's not that you'd expect to see, if the cursive dimensionality was a huge problem, all the length scales to just be the same.
Yeah.
To be revert to a prior, because all the points are so far away in space that there's no learning of length scales in there.
Yeah.
But you don't see that. You see the results make sense in an intuitive way. So doing things in these random Fourier features allows us to do these amazing high dimensional problems, but also gives us this flexibility to learn really complicated models.
Yeah.
So for example, in the malaria model, we have a term that's only that tells you what's the baseline level of malaria. We have a term that affects the intervention, so bed nets, and restricts that to only have a negative impact.
Okay. In the sense that more bed nets reduce malaria.
Or do nothing.
Yeah.
But they never increase malaria.
Because there'd be no causal.
Well, there'd be no causal mechanism.
So,
but sometimes with linear model and things, you can end up with these weird inconsistencies.
Yeah.
With the socio-demographic effect, like housing, electricity, again, they'll either do nothing or decrease malaria.
Right.
And then you have the environmental functions that have complicated forms that can both increase and decrease malaria depending on where they are, right? And so we can have this complicated additive model with each of these terms being a Gaussian process of its own, but put in random Fourier features. Yeah. And solve this in an unbelievably fast amount of time in Google's TensorFlow platform using GPUs. And you can solve one of these models in 5 minutes, 6 minutes. Yeah. Of course, you have to do a ton of cross-validation and tuning and all this. You have to be very careful with it, but that's down to the researcher, not the method. Just because you have to tune something doesn't mean it's an inherently bad method.
I think the use of these kind of techniques just comes back to the full process of conducting inference. It's not simply fitting a model; it's a matter of model building, model fitting, model checking, and then standing somehow over the whole thing and taking another look.
Standing in the process, and asking people on the ground, is this nonsense? Do we have to go all the way back to the start? But the random Fourier features also allows you. Because remember, I said that every positive definite function has a spectral tensor. It's a probability measure, which you can think of a probability distribution. And the first thing you can think about there is, well, could we just use mixture models to get any probability distribution?
You mean for the spectral density to
For
represent
spectral
it?
density.
Right.
And so Andrew Gordon-Wilson has done this.
Uh-huh.
And so this is a nice way forwards into creating nice spatiotemporal or very complicated spectral
Mhm.
densities. Again, the seminal work of Cressy, where he derived non-separable spatiotemporal functions from their spectral density.
Yes.
Again, we could just use the spectral density. We don't have to. Like using the spectral density does make life a lot easier in terms of formulating non-separable spatiotemporal functions or formulating different kernels.
Yeah.
And so there are added benefits with that. And so essentially, the new malaria mapping, the work we're doing now in mapping residual transmission is moving away from the more vanilla stuff to
Right.
giving the researcher the ability to actually put in biological plausibility in there.
Yeah.
Which is the direction we're going in. It's just to include more domain knowledge or mechanism into these models, so that and that's what we're kind of doing now inferentially, but we're trying to do more of that right now.
So before we run out of time, I think it would be worth just quickly talking about this related idea, which is that of trying to model at the biological or at the epidemiological level as a latent field, and then connecting that up to the observations. So this idea that we might model a surface of R naught.
Exactly, yeah. And this is huge, as in your work in serology, which is, you use the Gaussian process to model some latent parameter, which then feeds into a mechanism, which in your case is a Markov process.
Right. Yeah.
Some of the work being done at Imperial now with my student is, again, have a spatial field in there, but then have a network process on top that defines an independent cascade model on how networks progress. And we could do this for a large number of diseases. For example, for HIV, we can learn the force of infection parameter as a latent variable. Almost, you get a map of this parameter.
Yeah.
And then based on that parameter, you have a mechanistic model that then takes you to the end.
Right. So then the computational challenge, which is added on top of all the Gaussian process machinery, it becomes this one of converting something epidemiological and latent, like the R naught, into something observable through an epidemiological model, which can be quite expensive.
It is. And in the idea of malaria, the force of infection, or the vectorial capacity, is much closer linked to the covariates than, say, prevalence. So the idea is that you might get a better fitting model, which possibly you can, possibly you can't. I mean, considering Gaussian processes go through an almost infinite number of functions, a certain space, a Hilbert space of functions, that you have the choice of. Here, when you put it through the mechanism, you are implicitly reducing that size down, right? So sometimes you might conceive it might not be the best predictive power.
Yeah.
But what you do get when you do that is everything for free. And what I mean by that is, if you fit this joint spatial mechanistic model to, say, prevalence, well, we get the entire mechanistic model to play with, but calibrated correctly.
Right.
Which means we can figure out what asymptomatic loads are, what infection is. We can throw counterfactual type questions at it.
Yeah.
And so that is the direction that I think spatial mapping must go in, and will go in.
Right.
And it's already being done in various veins. In our simpler work, where you're throwing a discrete, continuous time Markov chain with a discrete assumption, and I'm throwing a independent cascade mechanistic model at it. But the idea is still, is to connect to a mechanism, and so the likelihood is it's more or less a mechanism, and then the process is still this GP or a stacking or a random Fourier feature or whatever your favorite learning method is in there.
Yeah.
And so this is the exciting part of the future that sort of we encourage people to join the MAP family and work alongside these exciting projects.
For sure. All right, well, let's wrap it up there and we can go get some lunch. In fact, lunch today, we're welcoming a couple of new research assistants in the group.
Yep.
So pop out for something good at the pub. But thank you, anybody who stayed watching this long. And
honestly, well done.
Yeah, hopefully we'll improve our delivery and range of topics. But thanks a lot also to Sam for
thank you very much
for participating in this first MAP podcast.